Okay, so good afternoon to all the dignitaries present here. So on behalf of my team, I'm going to present this topic. I'm Dr. Dibyendu Mondol, a faculty in Biomedical Engineering in JIS College of Engineering, and our topic is electrochemical study of graphitic oxide and reduced graphene oxide, emphasizing on their defect densities. So, can I proceed?
Yeah, proceed with your.
Okay, so So before going into the detailed work, first we must go through an introduction part. As we are talking about graphene and as the main topic of our project, or rather the research is graphene. So first we should know what is graphene. So most of the people here knows that it is mainly a carbon allotrope, where the carbon atoms are arranged in a monolayer manner in a two-dimensional honeycomb structure. Here, the electrons are present. The electrons that are present in graphene have no rest mass that mainly contributes to some of its unique features. To name a few, like anomalous quantum Hall effect, or absence of localizations, or it could lead to high electron mobility also, and that is also in room temperature. And due to all these things, these attributes to its extraordinary thermal conductivity. So if we can chemically modify graphene into graphene oxide, we can draw certain attention among the research community because of its innumerable applications in the field of sensors. Mainly, we are dealing, nowadays, we are mainly concerned with medical sensors and sensors for various other activities and researches throughout the world. Then we can go for various devices like field effect transistors for energy storage devices, because this graphene oxide has excellent thermal, electrical, and mechanical properties. Now here is the abstract of our work, which is given in a nutshell. So I'm not going into detail of this work, just I'm reading out the points where we have synthesized reduced graphene oxide from graphitic flakes. Then we had characterized this through various characterizing tool to name XRD Raman spectroscopy, FTIR, same analysis we have done. And we have seen certain characteristics of the composite of the material that has been so formed, which gives the footprint of graphene oxide and reduced graphene oxide. This is the pictorial representation of the complete procedure. Coming to slide number 5, it is nothing but the preparation stages that we have gone through for getting the reduced graphene oxide. I'm just elaborating a few points. Like first, we had done purification of graphitic flakes, and that is done by we use graphite powder and we have mixed that with hydrofluoric acid, and further it was decanted and it is washed with distilled water to make the pH neutral, because if we have to use for its variety of areas, so we must keep the pH neutral. And after that, we have done ultrasonication for proper mixing. Later on, acetone was added and it was allowed to get suspended, and it was dried in an oven around a temperature 80 degrees centigrade. Next stage, how graphitic oxide has been produced. So it was artificially developed by treating this purified graphite flakes with oxidizer. It could be sulfuric acid or nitric acid. And this only helps in removing uh, a particular electron in the reaction with the graphite. Then coming to how we have converted this graphitic oxide to graphene oxide. So for that, we used a very common step, that is we exfoliated this graphene oxide via ultrasonications, and that also done with vigorous stirring, which changes its stacked structure into a layered stacks. And finally, we got the reduced GO, which was GO was treated with hydrogen hydrate, and the solution was maintained at 100 degrees centigrade for around 24 hours. Now, finally, coming to the result and discussion, first we will go through the XRD analysis of the uh, material that we have developed. So first we can see the XRD peaks of graphene oxide, that is in blue, and reduced graphene oxide in red. So characteristic peaks of this graphene is clearly visible in both the plots, and those were verified with JCPDS card. I mean, we all know it's Joint Committee on Powder Diffraction Standards. So here we can see a table which has been provided for various 2 theta values, and the Miller indices HKL are given for each corresponding peak. So 2 theta is nothing but the angle between the transmitted beam and the reflected beam. So this is the first sign that graphitic oxide and reduced graphene oxide has been produced in the material so that we have synthesized in lab. Now coming to a very important parameter, that is Raman spectroscopy. Raman spectroscopy have also shown that, has also established that there is a footprint of graphene where we can see D, G, 2D and D plus G bands are obtained also and we know that in Raman spectroscopy, basically for graphene, we must have D and G bands. So if we can find the ratio of intensities of these D and G bands, we can get the defects, the amount of defects that are present on graphene structure. So the G band is a result of in-plane vibration of the spo2 bonded carbon atoms, whereas the D band is due to out of the plane vibrations that are attributed to the presence of structural defects. So here also we can see that those D and G bands are present. So from here what we can do, as I told, we can find out the defect density. Excuse me. So the ratio of the two peaks, as I just told, of the intensities of D band and G band gives the measures of how much disorders or defects are associated with the samples. So as we can see from the slide only, so depending on the defect density, two most empirical formulas we can write with, which can be related with the intensity of D and G with LD. So what is LD? LD is mainly LD is the distance between the two defects. It's the length between the two defects, and that is given by nanometers. So the two defects, the ratios are like we can say ID by IG, which there is certain different equation for those are for low defect density zones, and for high defect density zones, the value of ID and IG or the formula of ID and IG ID by IG differs. So as I told, what is LD? LD is the average distance between the defects, and C lambda and D lambda are nothing but constants. So IG does not depend on disorders as IG doesn't depend on disorders as G peak relates to the relative motion of this spo2 carbon atoms. But if this LD is less than 3 nanometer, due to reduction of this sp2 domain, more distortions will occur in these hexagons of the honeycomb lattice that we know are present in our graphene lattice. So ID decreases, which in turn decreases the value of ID by IG. So hence, it becomes proportional to LD, as we can see from the second equation. So it is said to be in the high defect density zone. But if this LD is greater than 3 nanometer, the value of ID by IG becomes inversely proportional to the square of LD. That is, we can say that's the low defect density zone. And in the table, we can see the peak positions are given, which corresponds to the band associated. So in this case, the ratio of ID and IG becomes around 0.992 for graphene oxide, and it's around 0.89 for reduced graphene oxide. And if we can fit these values in value of ID and IG, we can calculate the LD, and that was found around 10.05 nanometer and 9.54 nanometer for GO and RGO respectively. So therefore the samples prepared, we can well fit that samples in nanocrystalline zone with a very low defect densities. Now coming to FTIR study. So here also we have seen at certain positions we have got the peaks for GEO and RGO. So I'm not elaborating this slide as everything is written on the slide only, and we know which are the places where the graphene oxide, where we have got the peaks of graphene oxide or reduced graphene oxide, and each of the peaks at various wave numbers represent some chemical changes. Suppose if we discuss few of them, the peak that has been observed in 1120 per centimeter, it is due to hydroxyl ion vibration. The peaks that are in 2928 per centimeter or 2859 per centimeter, they are mainly attributed to the carbon-hydrogen stretching vibration of the amino group. So there are various chemical analysis for each of the peaks, and we have studied that, we have tallied with literatures, and we have found that these are the phenomena which can occur due to the presence of graphene oxide or reduced graphene oxide. Same here also, the blue one is for graphene oxide and the red one is for the reduced graphene oxide. This is the electron microscopic structure. Here we can see the figure A and figure B. These are for GEO, that is graphene oxide, where we can see there are certain disoriented clustered shapes, but they are crystalline in nature and there are lots of open spaces, and these are due to mainly the result of oxidation. And figure C and D, these are the figures of microscopic figure of reduced graphene oxide, and we can see there certain plate-like structures has been formed. So these planar structures are mainly seen in reduced graphene oxide. So this is also a signature of a successful reduction of graphene oxide into its reduced form. And the minimum particle size that are found in the sample is around 200 nanometer. Now coming to dielectric analysis, as we are moving towards electronic purpose of this material only, so we must focus on dielectrical permittivity. So what is dielectrical permittivity? It is nothing but the ability of a substance to hold any electrical charge. So if a substance can hold a humongous amount of charge, so that substance can be placed suitably, or it can be easily be switched to some electronic devices or biological devices which can act as electronic device, like which we can use in for bioelectronics or biomems or biosensors. For all this purpose, we can use this kind of materials which have high dielectric permittivity. So in both the samples, as we can see from the plot, the dielectric permittivity decreases with frequency, and mainly it approaches almost to a constant value while the frequency is going in the higher side. So the dipoles have enough time to rotate for this alignment with the electrical field at lower frequencies, and which causes a high value of dielectric permittivity at the lower frequencies. So we can see at lower frequency around 35 to 40 hertz, graphene oxide attained the dielectricity value of around 4.4 in 10 to the power 6 power. But while the frequencies has been increased to around 1 kilohertz, the dielectricity has been reduced considerably to 1.7 into 10 to the power 5. Likewise for RGO also. So we can see for lower frequency, the dielectric permittivity of the substance that has been created in lab is considerably much higher. Now, coming to the resistivity analysis. So electrical resistivity of both the samples of GEO and RGO has been measured. So resistivity of GEO became very high because after oxidation, the interplanar spacing increases, which in turn mainly alters the SpO2 bonding. So that the network that has been created by this SpO2 bondings, those get disrupted totally. So but in case of RGO, resistivity value becomes almost 14 times less, as we can see from the slide, compared to that of GEO. that is really due to the restoration of this spo2 network, because we have removed hydroxyl group from the structure, and thus carbon-carbon single bond, carbon-carbon double bond has been formed. For that reason, the resistivity has been decreased at an alarming rate. Now, this is
Yeah,
the
so you
conclusion.
just make sure you have 1 minute left. Just
Yeah,
make sure
sure. I
go
have
to the.
reached conclusion. So this is the conclusion. We have completed the whole process in a lab, and whatever we have done that has been summarized in the conclusion. I'm not elaborating this part, but another thing which I must tell, that the graphene or graphitic oxide or graphene oxide, whatever we can get from by this method, that can be utilized both in electronics industry, in energy, space industries, in thermal industry, as well as we can switch over to bioengineering and biomedical industries also, because we are switching more towards sustainable products. And while we are talking about anything which are to be implanted in a body, that must be of minimized size, that must be logical, and it must be cost effective. This is the future prospect. I'm not again reading it out, but we can extend this research into medical applications. So such is the prospect of graphene nowadays, and the future research ideation is summarized here. Thank you.